All right, so Theorem 2.9 is a theorem that's used in the proof for Theorem 2.8. So the book has them a little bit reversed in order there. So the inverse of a product theorem says that if A and B are invertible of size n, that means compatible for multiplication purposes, then A times B is invertible, and the inverse of A times B is B inverse times A inverse. So the fact that, so if we find what the inverse of AB is, that takes care of checking to make sure that AB is invertible. So if we find the inverse, that kind of takes care of the problem. So now we are going to have to prove that provided that the matrices are nice and invertible and everything else happens the way we want it to, we have to show that, prove that the inverse of AB is B inverse times A inverse. Okay, so in other words, we have to show, so we must show that the inverse of AB is B inverse A inverse. Well, in order to show this, all I have to do is check the two conditions. So I have to check to make sure that this multiplied with this from the left is equal to the identity, and also we have to make sure that this multiplied with this from the right is the identity. So the first multiplication, AB times B inverse A inverse. Now let's see. I have to show that this equals the identity. So I'm not going to write it equals the identity yet, because I don't know if it does. So I have to continue, and I have to use some properties of matrix multiplication in order to make it to this equals the identity. So the first thing that pops to mind is the associative property, which means I can move the parentheses and group these in any way I want. So what I'm going to do is I'm going to group the B times B inverse multiplication together. So I'm going to multiply those two guys together first. So all I did is I changed the parentheses. Okay, so this now equals, I know that B inverse is the inverse of B, right? So I'm assuming they're invertible, and the notation, I know what the notation means, so I don't have to explain the notation. B times B inverse is the identity matrix times A inverse. It doesn't matter which way you multiply times the identity matrix. So you may as well multiply the first two together. So that gives you A times the identity. The definition of the identity is that you get back A, and then you carry out the A inverse. Okay, so now A times A inverse again is the identity. So I started with the two matrices I was trying to show that they're inverses of each other with left multiplication here, and I worked my way out to the identity. Now, the second condition will have that has to be satisfied is that I have to check that B inverse A inverse times AB also equals the identity. Let me make sure if the camera can see that. Okay, so again, the same process. I'm moving my parentheses, so B inverse times B, that should be an A inverse. A inverse A times B. So I am using the associative property of multiplication of matrices, and I can group those any way I want. Now, B inverse, A inverse times A is the identity times B. So now I can group the multiplication by the identity with anybody, so I could multiply it by B inverse, it doesn't matter. B inverse times the identity is B inverse times B, B inverse times B is the identity, and so I checked that this direction of multiplication works as well. So now that both multiplications equal the identity, I can conclude, so this is my conclusion, AB, the inverse of AB, the inverse of AB is B inverse A inverse. Or, in other words, that also means AB inverse is equal B inverse A inverse.